Stars and planets. The universe is full of them, some of the biggest things ever to exist, and both of which have pretty interesting backstories. Let's begin with planets and what makes them up. The inner planets were created by a collision of rocky bodies in the early solar system. Mercury, Venus, Earth, Mars, and the asteroids, the celestial bodies we know today, are composed of heavier elements like aluminum, iron, silicon, sulfur, carbon, and oxygen, which were pulled together to the inner solar system by gravity and created by supernovas. Lighter elements like hydrogen and helium were blown together by solar wind to the outer solar system, where they were attracted to rocky bodies and formed the gas giants Jupiter, Saturn, Uranus, and Neptune. Now let's talk about where these elements came from. We touched briefly on the topic of supernovas, but there is quite a bit we need to talk about before we get there. All stars start out in a stellar nursery, a massive cloud of electrons and other space bits. The cloud of space bits will eventually be hit by a shockwave of some fashion, and thus condense itself to form a protostar. A protostar is a small, heat-producing mini-star that lacks the capability to perform nuclear fusion due to its current lack of energy and mass. The protostar will then begin to heat up even more, creating more and more energy, eventually transforming into what we call a main sequence star, aka our Sun, thus gaining the ability to perform nuclear fusion. As the main sequence star goes throughout its lifetime, if it has less than 5 times the mass of our Sun, it becomes a red giant. A red giant is a star which no longer has any reactions in its core, and begins to shrink, but reactions in the atmosphere still occur. As fusion in the atmosphere continues, a shell of gas forms around the star, called a planetary nebula, which also lasts about a few thousand years. Once the planetary nebula dies out, the star becomes a white dwarf, which no longer has any fusion and only emits light due to residual energy. After the light is expended, the white dwarf becomes a black dwarf, which no longer emits light, and is only visible when in front of another light source. Taking a few steps back to the main sequence star, if it has more than 5 times the size and mass of our Sun, it becomes a red supergiant, a massive star that burns brighter than a red giant due to its immense heat and mass. Through nuclear fusion, red supergiants will combine lighter elements like helium and hydrogen to create things like lithium, beryllium, carbon, boron, nitrogen, oxygen, sulfur, phosphorus, silicon, vanadium, titanium, scandium, calcium, manganese, iron, cobalt, and nickel, ending in the last 3. Eventually, the star will run out of energy and cease to perform nuclear fusion and collapse in on itself, thus exploding and going supernova, which is an incredibly enormous explosion with incredible amounts of energy. In 1 second, a star going supernova will release more energy than our Sun will in 10 billion years. In doing so, it creates many elements, including tin, indium, cadmium, silver, scabrium, tungsten, molybdenum, neodymium, yttrium, strontium, barium, and pretty much everything on the periodic table. Now, if the star has at least 25% the mass of our Sun before going supernova, it will most likely collapse again to create a black hole, an incredibly dense ball of gravity more or less. But if the star has less than 25% the mass of our Sun, it will become a neutron star, a star in which the protons and electrons cancel each other out and the star is left with nothing but neutrons, and will then float in space forever, until eventually starting over again as a stellar nursery. This project was brought to you by Max Lau, Philong Tran, and Jennings Mergenthal.